Welcome back everyone. In this video, I would like to discuss about International Standard Atmosphere, and I will also let you know about how to calculate temperature, pressure and density of the atmosphere at a certain altitude. So let's get started. Aerodynamically, an aircraft can be defined as an object traveling through space that is affected by changes in the atmospheric conditions. Atmospheric conditions like temperature, pressure and density. So above the surface of the Earth at any given altitude, we need to calculate these conditions as they affect flight operations. Air is a fluid that can be compressed. So at the sea level, the density of the air will be more because it has been compressed by the air above it. This compression of the air is called as atmospheric pressure. In order to calculate the pressures at different altitudes, we need to have a standard pressure to be compared. So the standard atmospheric pressure at sea level is termed as 1 atmosphere, which is equal to 14.7 pounds per square inch, or 1.01325 into 10 power 5 Newton per meter square, or 760 mm of mercury. As we go higher in the altitude, the atmospheric pressure decreases because the weight exerted by the air above that surface will be reduced as we move higher. Now we'll take a look at variation of temperature along the altitude. Now we'll take a look at variation of temperature along the altitude. So we'll draw a graph between altitude versus temperature along the x-axis and the altitude over the y-axis. So we know that the temperature of the gas is directly proportional to average kinetic energy of molecules present at that region. So over the surface of the earth there will be more particle density than above the surface of the earth. Since here the particle density is higher, the temperature will be more, and as we go above from the surface of the earth there will be less number of particles over the region, so there will be reduction in temperature as we move higher. And there are some cases between the altitudes where the temperature increases from certain region to certain heights. So I'll draw the graph first between temperature versus altitude and the regions uh, between which the temperatures changes will be there. uh, 0. So in the x-axis we take temperature, and in the y-axis we go with altitude in kilometers. 0, this is 11, 25, 47, 53, 79, 90 and then 105. So from 0 to 11 kilometers there will be reduction in temperature as we move higher. As we move higher there will be reduction in temperature from 0 to 11 kilometers. And we know we have a term called lapse rate, which is represented with A. This indicates how much amount of temperature is getting deferred per kilometer rise in its altitude. We can also say that A is equal to dt by dh. So the lapse rate for 0 to 11 kilometers is around 6.5 Kelvin per kilometer. So lapse rate represents for kilometer rise in its altitude from 0 to 11 kilometers, there will be reduction of 6.5 Kelvin. Since we are saying there is a temperature reduction, we need to represent with negative symbol. So A is equal to minus 6.5 Kelvin per kilometer. And from 11 to 25 kilometers, this region is said to be as isothermal region, and here lapse rate will be 0. And from 25 to 47 kilometers, the lapse rate is around 3 Kelvin per kilometer. And from 47 to 53 kilometers is an isothermal region with lapse rate is 0. So from 25 to 47 kilometers, the lapse rate indicates for every kilometer rise in its altitude, there will be increase of 3 Kelvin in temperature. And from 53 to 79 kilometers, the lapse rate is around A is equal to minus 4.5 Kelvin per kilometer. From 90 to 105, the lapse rate is plus 4 Kelvin per kilometer. So now we'll take a look at why the temperature is not gradually decreasing from the surface of the earth towards the atmosphere, and it is changing in between as the temperature rise happens from 25 to 47 and 90 to 105. So we'll see why this happens. From 0 to 11 kilometers, the temperature is getting decreased, as I have said before. In the surface of the earth, the temperature is higher because the earth absorbs heat from the sun and then emits out from the surface of the earth. So this region is having more temperature than the above region. So as we move higher, the temperature is getting reduced, and from 11 to 25 kilometer, there will be constant temperature. It is known as isothermal region. From 25 to 47 kilometers, the temperature is increasing because this region contains ozone layer. Since there is a presence of ozone layer, there will be much heat surrounded over the region. So as we move above from 25 to 47 kilometers, there will be increase in temperature, and from 47 to 53 Kelvin, there is a constant temperature. It is known as isothermal region, and the lapse rate is 0 here. And from 53 to 79, it follows the same trend as the temperature reduces as we move higher from the surface of the earth. From 79 to 90 is an isothermal region again, and from 90 to 105 region, it is again increasing because this region is close towards the sun. So as a region close towards the sun will be having higher temperature, and the region away from the sun will be having lower temperature. So this is how the variation of temperature happens, and we need to calculate the temperature, pressure and density at different heights, uh, because it affects the operation of the flight. So the basic things we need to know from this graph is the variation of lapse rate and these uh, kilometers from which the variation happens. So we'll take a problem and we'll calculate the temperature, pressure and density at a certain height. So we'll take a problem and we'll calculate the temperature, pressure and density at a height of 14 kilometers from the surface of the earth. So to calculate the temperature, pressure and density at different altitudes, we need to know the formulas. There were mainly 4 formulas to calculate them. The first one is formula of Toussaint. That is T1 is equal to T0 plus A into H1 minus H0. And then we have pressure and density formulas depending upon the lapse rate. When lapse rate A is not equal to 0, that is when height range is between 0 to 11 kilometers, 25 to 47, and then 53 to 79, and then 90 to 105. So in these cases we need to use this formula. When A is not equal to 0, P1 by P0 is equal to T1 by T0 whole power minus G by A into R. And we need density formula too, so we'll calculate it right now. P is equal to rho into RT, we know that. So instead of P we'll substitute rho RT. P1 by P0 is equal to rho 1 RT1 by rho 0 RT0, which is equal to T1 by T0 whole power minus G by A into capital R. Since r is constant, we can cancel them, and rho1 by rho 0 is equal to this t1 by t 0 term will transfer to right hand side, then it becomes whole power minus 1. So rho1 by rho 0 is equal to t1 by t 0 whole power minus g by ar minus 1. And when lapse rate is 0, we cannot calculate pressures and density with this formula. So we'll take a is equal to 0, then we have the formula, that is p1 by p0 is equal to rho1 by rho 0 is equal to e power minus g by rt into h1 minus h0. So with these four formulas, we can calculate the pressure, density and temperature at any given altitude above the surface of the earth. So we'll calculate for a question like, so we have a question here, that is calculate the standard atmosphere values of pressure, temperature and density at a height of 14 kilometers. So the first thing is we need to draw that graph for better understanding of the problem. So we'll draw the basic graph for that. So this region will have 288 Kelvin and 0, 11, 25, 47, 53, etc. Since we were asked with 14 kilometers, up to here is enough. Now the first step is we need to note down the values of pressures, temperature and density at sea level. So these were standard values and we need to remember them. So the standard pressure at the sea level is 1.01325 into 10 power 5 Newton per meter square, and density is 1.225 kg per meter cube, and then temperature is around 288.16 Kelvin. So these three values were standard values at the sea level. So we'll take these values for every problem as a base values. So P0, Rho 0 and T0 values were fixed for every problem. And then the value of R is 287. So in case of lapse rate, we need to take in terms of meter. We were actually I have told that lapse rate is around minus 6.5 Kelvin per kilometer. So we need to take in terms of meter. So minus 0.0065 Kelvin per meter. We need to substitute this value here for A1. That's so now we'll calculate it. The first step includes the formula of Toussaint. So T1 is equal to T0 plus A into H1 minus H0. Since we were asked with 14 kilometers, we need to calculate the temperature, pressure and density at 11 kilometers first. Since we are having the isothermal region, the temperature at 11 kilometers will be equal to the temperature at 14 kilometers. So from that temperature, we need to calculate pressure and density values at that region. So I'll explain with the problem right now. So T1 is equal to T0 plus A into H1 minus H0 is the Toussaint formula. So T0 is the temperature at the atmospheric level, which is 288.16 Kelvin, plus lapse rate is minus 0.0065 Kelvin per meter, and we'll multiply with heights. Height is, we need to take in meters. So 11 kilometers is nothing but 11,000 meters, minus 0. So we'll calculate it, which is around 288.16 minus 71.5. So T1 is 216.65 Kelvin. So we'll note it down here. So the temperature here is T1 is equal to 216.65 Kelvin. So we got the temperature at 11 kilometers. Since it is an isothermal region, the temperature will be same at 14 kilometers too. We need to calculate the density and pressure values at 11 kilometers because these values act as base values for calculating pressure and density at 14 kilometers. So T1 is equal to 216.65 at 11 kilometers, and at 11 kilometers we need to calculate pressure and density. So P1 by P0 is equal to T1 by T0 whole power minus G by A into capital R. So T1 is 216.65 divided by T0 is 288.16 whole power minus 9.8 by minus 0.0065 into 287. So P1 is equal to 216.65 by 288.16 is nothing but 0.7518 whole power. This minus and minus will get cancelled, and the ratio is around 5.25, 5.253. So P1 is equal to this P0 term will be transferred to right hand side. P0 is 1.01325 into 10 power 5. So 0.7518 whole power 5.253 is 0.2234 into 1.01325 into 10 power 5. So P1 is 0.226 into 10 power 5 Newton per meter square, or P1 is equal to 2.26 into 10 power 4 Newton per meter square. So this is the pressure at 11 kilometers. Also we need to calculate density at 11 kilometers. Rho 1 by rho 0 is equal to T1 by T0 whole power minus G by AR minus 1. Since T1 by T0 value is 0.75, we'll substitute directly. Whole power minus G by AR is 5.253. So minus G by AR minus 1 becomes 4.253. So rho 1 is equal to 0.7518 whole power 4.253 is 0.2971 into rho 0 value we need to multiply 1.225. So rho 1 becomes 0.3639 kg per meter cube. So we have calculated temperature, pressure and density at 11 kilometers. Now we need to calculate them at 14 kilometers. So at 14 kilometers we take these values as base values because we have the formula P1 by P0. We need P0 as base value for first case, and here at 14 kilometers we need to take P2 by P1, where P2 is at 14 kilometers and P1 is at 11 kilometers. P1 is at 11 kilometers. For rho 2 is at 14 kilometers and rho 1 will be at 11 kilometers. So now 14 kilometers we have the formula of P2 by P1 is equal to rho 2 by rho 1, which is equal to e power minus g by RT into H2 minus H1. I have just changed P1 and P2 as P2 and P1, that's it. So this is the formula for calculating P2 and rho 2. And so first thing is P2 is equal to P1 into E value is 2.72 approximately, whole power minus 9.8 by 287 into what is the temperature at 11 kilometers. We have calculated as 216.65. So write it as 216.65 H2 minus H1. H2 is nothing but 14 kilometers, so 14,000 meters minus H1 is 11,000 meters. So write it here as P2 is equal to P1 into 2.72 minus G by P1 we have calculated it as 2.26 into 10 power 4. We'll substitute it here. 2.26 into 10 power 4 into, so this is the value of pressure we have obtained from calculation. So E power minus G by RT into H2 minus H1. H2 is 14,000 meters and H1 is 11,000 meters. So 14,000 minus 11,000 is 3,000, and this calculation is 0.0001576. So after simplification, 2.72 power minus 0.4728 is 0.623 into P1. So we'll get P2, and then we have rho 2 by rho 1 is equal to E power minus G by RT into H2 minus H1. So this RHS term is same, so we can directly multiply rho 2 with rho 2 is equal to rho 1 into this whole term, that is 0.623. So rho 1 is 0.3639 into 0.623, which is equal to 0.2267 kg per meter cube. So we have obtained the pressure, temperature and density at an altitude of 14 kilometers. Therefore T2 is equal to, since the temperature is same along the isothermal region, T2 is equal to 216.65 Kelvin, P2 is equal to 1.408 into 10 power 4 Newton per meter square, and rho 2 is equal to 0.2267 kg per meter cube. So we have calculated it easily for 14 kilometers. What if we were given around 31 kilometers or something? So for that we need to take 0 to 11 kilometers as the first basic value. We need to calculate the temperature, pressure and density at 11 kilometers first, and then instead of taking 14 kilometers we need to take 25 kilometers as the as a second base value. So P2, T2 and rho 2 should be calculated at 25 kilometers, and then we need to take these values as base, and then when we need to take the 31 kilometers as P3, T3 and rho 3. So here we need to use Toussaint formula again to calculate the temperature. In this case, in this second case, we haven't used Toussaint formula because the temperature is same along the isothermal region. So from 25 to 47 kilometers, we need to use the Toussaint formula again to calculate the T3, and then we need to calculate P3 and rho 3 as we have done with the formula here. So I hope you have learned something new today. Thanks for watching.